Welcome to video 3.1b about energy conservation. Now that we know the different types of energy, let's talk about how they relate to each other and what effect that has on solving some problems. The most important thing about energy is the first statement written here. Energy cannot be created or destroyed. It can only change its form. So when we talk about energy production, we're really not talking about producing energy out of nothing. We're really talking about taking stored energy and changing it into a type of energy that we want, usually electrical energy, because of all of the gadgets we have around the house. If we are looking at a system which includes all sorts of different items that are working together, if we have an isolated system, then the change in energy is zero, which again goes along with the first statement. Because we are not creating or destroying energy in an isolated system, there's no input or outtake of energy, so it has to all remain the same. This gives us the most important equation of the unit, which is that the initial energy is equal to the final energy. So the total amount of energy that we start with in our process must be equal to the total amount of energy that we end our process with. This has huge implications to life. For example, one of the things is that the amount of energy that existed in the universe at the time of the Big Bang is still equal to the total amount of energy that we have now in the universe. It's just all in very different forms now than it was then, and it will continue to cycle through different forms throughout the life of the universe. But the key is that the totals remain the same. Let's take a minute and take a look at a couple of examples of this with some simulations. Let's start with this. We have a series of 3 different springs, and we can hang masses on the springs. Let's take a 100 gram and we put it on spring 2. Obviously, the spring begins to stretch, so we have elastic energy here, and it goes back and forth and up and down a bit. And it will continue this until friction wears it down and it slows down. Let's put the same amount of mass onto spring 3. Now I can change the stiffness of spring 3 to see how this looks, because notice they're both 100 grams on spring 2 and spring 3, so they're going to stretch the springs the same amount. If I change the strength of spring 3 to make it harder, notice that the same 100 grams does not allow the spring to stretch as much as it did before. This gets back to our elastic potential energy based on the spring constant or the spring thickness or softness. Now, let me go ahead and show you the energy here. Let me get rid of friction because we're going to ignore friction for the moment. Now, if we take a look at this, we're looking at the energy of spring 3. We have a total amount of energy here on the graph, and notice that it's mainly blue. At the moment, it's a lot of gravitational potential energy because it is stretched a little bit. And we've got a little bit of elastic potential energy, a little bit of thermal because I hadn't turned the friction off yet. Now let me stretch it. And I stretch it a lot and my total energy changes, but when I let go, notice that my energies are changing super fast here. In real time, this is what's happening with my energies, but the total amount is staying the same. So let's slow that down a bit. So you can see here, without friction, there's no thermal energy. There's kinetic energies going up and down, gravitational potential energies going up and down, and elastic potential energy is going up and down with the spring compressing and expanding. However, the total amount of energy remains the same. It's just the relationships between, or how much of each we have, that changes. And as it slows down more and more, it will change the ratios of them as well. But nonetheless, you can still see that the total amount of energy before we started moving is still the same total amount of energy after we started moving. Okay, let's take a look at one other example as well that is not elastic potential energy, but definitely gravitational potential energy and kinetic energy. Over here, we have our cool skateboarder dude, and we've stopped him midway on his track. And you can see on the bar graph over here on the right that he's got a little bit of kinetic energy because of when I stopped him, he had some kinetic energy, lots of potential energy, a total amount of energy here. Now, if I have him start moving again, we can see that as he goes up, his potential and down, his potential and kinetic energy continually change back and forth, but still the total remains the same. So at the very bottom of the path, his kinetic energy is the highest, and then at the top of the path, his potential energy is the highest. Notice that at the bottom of the path, he still has some potential energy. That's because the 0 point is not the ground, but the bottom of the rink here. Now I can bring the rink down to the ground. And then notice that the potential energy basically goes to 0 as he gets to the bottom, and kinetic energy still goes to a maximum at the bottom. And again, potential energy. Now, this would never happen in real life because there is friction, but we've turned off friction here to see this. The key is that energy is being conserved, so potential energy is being changed to kinetic, and kinetic is being changed to potential. So now let's take a look at a couple of examples of conservation of energy, and let's start with a skier at the top of a hill. Let's say that the hill is at an angle of 35 degrees. We've got a skier dude up here at the top of the hill, and the top of the hill is let's make it bigger, is 15 meters tall. Because this is on snow and ice, we're going to assume that the force of friction is 0. If I want to know how fast is the skier going when he reaches the bottom of the hill, if I were going to look at that with kinematics equations, I would have to take into account the angle of the hill, the mass of the skier, the amount of the initial speed, the final speed, and all sorts of other things like that, F equals ma, and to find the acceleration and everything else. However, if we use this and try and solve this in terms of conservation of energy, lots of stuff goes away and it becomes really super easy. So keeping in mind that our key equation is the total energy at the beginning has to be equal to the total energy at the end. If we make the assumption that the skier dude sitting there at the top of the hill and not moving at the moment, then at the beginning they have potential energy. And at the end they will have kinetic energy. So the potential energy at the beginning is going to be mgh. The kinetic energy at the end is going to be 1/2 mv squared. Well, look at that. We don't even have to worry about what the mass of the skier is. It's irrelevant if kinetic energy is completely being formed from the potential energy that we had. So we go ahead and solve this for v. V then is equal to the square root of 2gh. And 2 times 9.8 times 15 gives us that the final velocity of the skier at the bottom of the hill is 17.15 meters per second. Super quick and easy when we use energy conservation. Again, you could solve this with kinematics, but you're going to save yourself a whole heck of a lot of trouble if you do energy conservation. Let's look at another one. Let's say that we are firing a Nerf gun. When you shoot something with a Nerf gun, you're essentially compressing a spring and then you're allowing it to release and shooting a foam bullet. Let's say that we have our spring here, nicely compressed. We have our foam bullet. And to begin with, we know that the spring constant is 40 newtons per meter. So it needs 40 newtons to compress this spring by a meter. Obviously, these springs aren't a meter long, but it's still the units that we use. The mass of the bullet is 20 grams. The question is, how fast will the bullet be going when it is shot out of the gun? In order to do this, we want to keep in mind that, again, we're going to use the same thing. The energy at the beginning is going to be equal to the energy at the end. Here, the beginning energy is elastic potential energy. So it's elastic energy, and at the end, it is going to be kinetic energy. Elastic energy, remember, has the form of 1/2 kx squared. Kinetic energy has 1/2 mv squared. We can cancel out the 1/2s, solving this for v. V is the square root of kx squared over m. So we know k, we know m, now we need to look at what x is. X is what is the amount the spring has compressed. So if this spring, typically all by itself, sits out like this, then the distance between where it is in its normal position and where it is when it's compressed is our x. And in this case, our x is going to be 5 centimeters. Keep in mind that we have to have the units all work out here. So K is in newtons per meter, M is in grams, so we're going to have to change that to kilograms, and X is in centimeters, so we will have to change that to meters. So we do that as we plug these in, and we end up with the square root of 40 times 0.05 squared over 0.02. 0.05 because we have to get to meters, and 0.02 because we have to get to kilograms. Calculating that out, we find out that the bullet leaves the Nerf gun with a speed of 2.24 meters per second. Again, super easy when we use conservation of energy. We don't have to worry about initial and final velocities. We don't have to worry about time. We don't have to worry about accelerations. We just can do energy conservation. This particular speed for a Nerf gun bullet is really, really tiny. They actually launch at a much faster speed than this, but it gives us the idea of energy conservation. So keep in mind this key equation here is how you're going to solve most of these problems. Now, it doesn't necessarily mean that all of the time there's only going to be one kind of energy at the beginning and one kind of energy at the end. You can have more than one kind of energy at the beginning or at the end. You could have potential energy, gravitational potential energy. In this, for example, we could talk about how high it is off the ground. So you could have more than one energy before or after. With this, you should have enough information to solve the conservation of energy problems. So, bye for now.